right, good morning, good afternoon, good evening, depending on when you're watching this video. This is considered our fourth lecture of the course for Intro Statistics. Today, what we plan to cover we'll go further into numeric summaries. So our last lecture, we talked about using the mean and the standard deviation, and also the empirical rule. Okay, so I guess I should write that there. And empirical rule. All right. So pretty much where we're coming from is first in chapter 1, we're just talking about what is data, what's numeric, what's categorical, and then of course always thinking about the important questions as far as where's this data coming from, who collected it, when was it collected, are they trying to establish a cause and effect relationship, and then we get into visualizing the data. Okay, histograms, bar plots, all that, dot plots, and with these plots, we're trying to visualize and inspect and say, hey, the center, the typical value is about here, the variation's about here. But now what we want to do is actually be a little bit more precise about what we mean about center and standard deviation and spread around the mean and things like that. And so that's where chapter 3 comes in and says, well, let's talk about numeric summaries. Okay, so last time we talked about using the mean here. And so as far as like looking at a graph, we visualize the center, but the mean is just a good old arithmetic average. So in class, I said, hey, here are 6 rent amounts for 4-bedroom homes in Moore Park. And what you have here is the the typical rent amount. So if you're gonna if my friend's gonna move to Moore Park and they want to rent a 4-bedroom home, and they want to know, well, how much are they going to spend? I'm going to say around $4,465 a month for rent, plus or minus something, right? And so we did an example here. I did a simple example there, and of course I showed you how we can compute the mean and StatCrunch. And so in this example here, we were just comparing home run totals for hitters in the American League versus home run totals against for hitters in the National League for baseball. So here American League had 18 and National League had 16 and a half. So I mean, on average, it's kind of telling you that the American League are better, are hitting a higher number of home runs on average. And of course here I also showed you in StatCrunch how before we had numeric summaries, we would be looking at this histogram here, or these 2 histograms here, and we'd be trying to pinpoint where we try to estimate where the center is at, And so now what this green line is, now we introduce the numeric summary for the center. And so these are the averages here. So we get to kind of visualize where this mean is located on our histogram. And you can see, I mean, if this green line weren't here, you'd probably pick somewhere around here as being the center. But you see here, the center is 18 home runs, and here's about 16.5 home runs for the National. And then, of course, very briefly, we talked about standard deviation, and I still haven't fixed it, but it should be -1, okay? And so, kind of what we said there is, this don't be intimidated by this notation here or by this formula. We really just need to understand what it's doing. And so what I try to point out is this is just really an average. And what is it an average of? Well, inside the radical, what is it an average of? Well, we're taking all these distances from the mean, and then we're squaring them, and then we're taking the average of those. So what we're doing is we're taking the average square distance of our observations from the average. So we're just trying to, what's the average square distance? If I were to pick any home run total, what would be the average square distance between the observation and the total and the average? So what we do here is we take the square root. Okay, so what the square root is, right, is telling us it's the standard deviation. And the standard deviation is the number that measures how far away the typical observation is from the mean. Okay. So so in this example, I just showed you the table and just gave you the gist as far as how this is calculated by hand, and how this gives us, this right here stands for sample variance, and this right here is what we call the sample standard deviation. Okay, so what that 1.47, it means, let's just say these x's here represent, you know, number of siblings a person has. So we're just saying this 1.47 is how far away the typical number of siblings is from any response for number of siblings. Okay, so it's kind of a funky interpretation. So that's why we like to use the empirical rule, so we can get a better interpretation of this standard deviation. Okay, so so in these examples I came here and I said, okay, well, this is just an example of standard deviation increasing, and then we went into graduate admissions and we were studying you know, the GPA, how if there's a kind of pattern between GPA and where one sits in the classroom. Okay, and so what we did here, where we left off here, was with the empirical rule. Right, so here we're going to start getting into the new topic, which is z-scores. Okay, but really quickly, what this empirical rule is saying is that, look, let's say you collect all your observations, and these are for numeric variables, okay, and you create this histogram. Okay, you create this histogram. It doesn't have to look like this, but, you know, I mean, we've seen a lot of different histograms by now. I mean, no two look alike. Okay, but, you know, what they're saying is that, you know, you make a histogram and maybe it looks something like this. And so this is like a rough guideline, a rule of thumb. It means, well, between, if you have your sample mean, that's what this x bar means, and you have your s, this standard deviation, that's what that means. It means, look at your sample mean, okay? Add standard deviation here, subtract standard deviation from there. And in between here, in between these two numbers, right, where everything's blue here, roughly 68% of your observations should fall, right? So if this were random amount, and if S was the standard deviation of the random amount, then I can do standard deviation plus the average, standard deviation minus the average, sorry, average minus standard deviation, and I should roughly expect 68% of the random amounts to be in here. Okay, so so in this example, we were just working on here we were working on seat location and GPA, and so we did some examples here in class, and we wrapped those up. Okay, but here, I mean, just going back here really quickly, you know, as far as the empirical rules, kind of you're looking at all the data at once. So for example, for the middle row, what this is saying is, okay, well, you know, if I had 100 students sitting in the middle rows, I would expect 68% of their GPAs to fall somewhere between 2.47 and 3.33. Okay, and so so because we're doing a 68% rule. Okay, so that means what that also implies is that if we do 100% minus 68%, that 32% of GPAs will be outside of those intervals. So a lot less number of them will be larger than 33 or smaller than 2.47, right? And so what this kind of tells you is, for these empirical rules, if we go back here really quick, like if we're doing a 95% empirical rule, it's saying pretty much all the values between sample mean minus 2 times the standard deviation, all the way to sample mean plus 2 times the standard deviation, all of these are what we should expect to see, because 95% of our observations should fall in here. These are kind of like typical values. So pretty much any point that falls in here is of no more distance away than 2 standard deviations, right? Because the distance from here to here is two standard deviations, and the distance from here to here is also 2 standard deviations. So everything in here is kind of typical. And so what that means is this green stuff right here, okay, this green stuff, right? Or anything beyond here or beyond here is definitely unusual, okay? And if I have an observation that falls in here, it is more than 2 standard deviations greater than the mean. And if I have an observation that falls here, then I have an observation that's more than 2 standard deviations smaller than the mean. And so these things we would call, you know, weird or unusual observations. And so what if I just want to look at one observation and I want to kind of determine whether it's unusual or weird, right? I don't want to look at all of them, say I just want to look at one. Okay, maybe we have a histogram or a dot plot and we see a couple points that they look like they could be outliers, right? They're potential outliers. What's one way we can put a numerical summary and determine whether that's an outlier or not? Okay, so what we introduced now is the z-score, and the z-score we're going to see over and over again in our class. But what it does, it's a measure of distance from the average. Okay, so it says, how can we determine whether a single observation is unusual or weird? Okay, and it says standard units measure a value relative to the sample. Okay, so when we say a measurement converted to standard units is called a z-score. Okay, and the formula of this, the z-score of a value of x, is given by this quantity here. So pretty much, I mean, within a context, this is like x is like a rent amount for a single house. Okay, so let's say if we're talking about the Zillow data, the rent amount, right? This X bar here is the average rent amount for 4-bedroom homes, right? And so this new house comes out on the market and it has whatever rent amount. Okay, maybe it's like 6,000, 5,000, something like that. Okay. So what we do right away is we compare it to the typical value in the market, and we want to know whether it's reasonable compared to what's in the market or not. And so what we do is well, first we take the rent amount of of this new house, and then we compare it to the sample to the mean. Okay, so pretty much we just take the difference, right? We want to know what's the difference here. Right, and so this difference is gonna be, you know, maybe it's like $500 or $1,000 or $2,000 or it'll be negative $500 if it's smaller, or negative $1,000 if it's smaller than the average. But anyways, I mean, this number that we get, say the difference were 1,000. Well, is that a big difference in the context of this study, right? Is it a big difference, right? And if you may be thinking about rent amounts, right, for rent, like a difference in $1,000, like, yeah, that's a pretty big difference. But say we're talking about home prices, right? A difference in $1,000 for a price of a home is really nothing. Okay, so really, I mean, what determines a difference being significant? And so that's where we take into account the standard deviation S. Okay, because that's where we take into account S here, okay? Because S is the standard deviation, and so S, remember, it's the expected difference that we should see between any rent amount and the average rent amount, right? That's what the standard deviation is. Standard deviation of what? Well, the standard difference between any rent amount and the average rent amount. So we compare this deviation pretty much to the standard deviation, okay? And pretty much if this value is larger than 2 or less than -2, like -3, you know, then we're gonna say that this rent amount is weird compared to what's out in the market. Either it's way overpriced, right? Like, what's up with this place? Does it, right? What cool perks does it have with it? Or maybe it's way underpriced, right? Like, what's wrong with this place, right? That's what it'll get us there. Okay, well, let's see an example here, really quickly here. Okay. So so really quickly, I'll just go into StatCrunch really quickly, and what we'll do is there's this data set that's on nutritional data for fast food in 2017. Okay, so let me see if I can pull that up really quickly. Okay, so here we go. So this data set here for fast food, it says the data set was collected 2017. And so they're just looking at online nutritional information provided by fast food restaurant chains. And so they just pick different burgers, breaded chicken sandwich, grilled chicken sandwich, chicken nuggets, french fries, chocolate milkshakes. And from there, they collect the nutritional information. Okay, so the data set looks like this. Okay, so obviously, you know, we have a categorical variable, categorical, and then I believe the rest of these are numeric variables, right? And so what I want to do here is maybe I just want to look at burgers, okay? I want to look at burgers. See here, type, they have like chicken nugget, milkshake, breaded chicken. So let's just look at the burgers amongst all the fast food chains. And let's look at the calories per burger. And let's see if there's any burgers that have maybe perhaps really large amount of calories and really small amount of calories, okay? So how do I find these using StatCrunch? And there's a couple ways you could do it. You could sort this here. You could go here and then go sort, and they'll sort it and they'll take everything with it. Or we could just do a graph. Okay, we could do a graph, and we could do a dot plot, let's say. So let me do a dot plot for calories, and I want to group it by type, right? Because I want a dot plot for burgers, right? For burgers. So and type is where they have burger, milkshake, and all that good stuff. Okay, so let's go ahead and compute that right there. Excuse me. Okay, so if I look at this here we go here, okay? Here we go here. So down here's the burger. Okay, down here's the burger. This is for milkshake, grilled chicken, french fry, but here's burger. So right away, if I look out here, you might say, oh, that might be an outlier there. So let's click on it. Okay, let's click on it. And if you look at it, it's a burger with 1,240 calories. Okay, so a pound in an instant. Okay, and then down here we have this burger, which is which only has 140 calories. So if we want to find out which burgers those were, we could go here and say, oh, this is Sonic, the Supersonic burger. I guess that's going to have about 1,240 calories. And if we go down here, we have White Castle. Okay, and I guess this is the original something or other. It's a burger, only has 140 calories. So over 1,000 less, right? But these observations, are they unusually small? Right, there's a difference between being the smallest amount and the unusually smallest amount. So meaning we're talking about outliers. So our last class meeting, a lot of you were looking at the roller coasters and you're saying, yeah, these look like outliers for the wooden roller coaster. These look like outliers for speed for the steel roller coaster. Okay, so so what we get here is this. Okay, so if I go back here, let's just look at those single points. So now what I'm going to do is, this is actually the sample mean and the sample standard deviation. Excuse me. The sample mean and sample standard deviation for the calorie amounts for burgers. Okay, and really quick, I'll just go back and show you how I did that. Okay, so here I just did stat, and I did summary stats, and we're always doing columns here. Okay, and here I'm doing calories, and then I wanted to group by, once again, type, right? Because I want to get just the mean and the standard deviation just for the burgers. So I could do sample size if I want. I could do mean and standard deviation. Okay, and if I compute that there, then that's what I get here. Okay, so I pulled the information from right here. Okay, I pulled it from right here. Okay, so you see here, 69 burgers. Here's the mean, here's the standard deviation. Okay, so I think we did look at this data a little bit before, where remember Chick-fil-A, you only get chicken, and In-N-Out, you only get cow. Okay, so we're revisiting this data. So here's the mean, average number of calories for burgers. and this is the standard difference we should expect to see between the average calorie amount of 620 and any other burger calorie amount, right? That's standard deviation interpretation, right? So if I recall White Castle's burger with calorie amount of 140, okay, well, let's calculate the z-score. So this is the smallest, but is it unusually small, right? Is it like an outlier? Well, let's look at this difference in terms of standard deviation. So what the z-score is doing is, first I'm going to compare my observation. I'm going to compare 140 to the mean, okay? And if I take this difference, what I find is that it's negative 480.2. So what this tells me is that the White Castle's burger amount has 480 less calories than the average, okay? So just looking at that number there, do you think that's really, really far away to make this unusual, right? Right, or not? And so it depends. If I were to have a poll and have you guess and raise your hands, there would be varying answers, all right? It'd be pretty subjective, okay? But what we do to remove that is that we compare this difference to the standard difference we should expect to see. Because what this is saying, well, the expected difference, right, we should see between calories and the average calories, it should be around 277. Okay, so what we see is slightly larger than that, but how much larger is it? So that's why we just take the division here. So I divide these two numbers, I get negative 1.73. Okay. So when you convert your data to z-scores, they usually all go between numbers between -3 and 3 usually. So here it says White Castle's calorie amount is 1.73 standard deviations less than the average calorie amount for burgers. And the reason it's less is because there's a negative sign here. Okay. So now, so the thing is that, well, the thing is now, so we know that it's 1.73 standard deviations less than the average calorie amount. Well, is this weird or not? So what we do is we recall the 95% empirical rule, okay? And we say here, well, z-scores further than 2 standard deviations away from the mean are considered unusual or weird. Okay, so that means so 2 standard deviations means that the z-score is like 2 or 2.5 or 3 or greater, or it could be like -2, -2.5, -3, -4, or smaller. Remember, it's like negative direction, right? Right. So that's what it means. So in this case, negative 1.73, right? It's not less than -2, right? It's actually in between -2 and 2, right? So in this case, we would not conclude that it's weird. Okay, it's not weird. Okay, so this calorie amount, it is small, right? It is small. It is the smallest, but it's definitely not considered perhaps an outlier here. Okay. So one more example. If we look at the Sonic Burger, okay. So Sonic Burger, it had the largest amount of 1,240, right? And if we go back and look at that, the graph here. Okay, I mean, as far as the distance goes, right, it was pretty far out there, right? There's a little bit of space there, right? So maybe this has more potential for being a weird or unusual observation, right? Not only is it the largest, but it's also weird, right? It's not consistent with the data. All right, so if you go here, we do the same thing, okay? We compare the difference of the calorie amount with the average calorie amount. And we say that, well, the Sonic Burger has 619.8 more calories than the average calorie amount. Okay, so we compare that to the difference that we would expect to see, the typical difference, and what we get roughly is 2.24. So in this case, we say Sonic's calorie amount is 2.2 standard deviations greater than the average calorie amount for burgers. Okay, the reason it's greater is because it's positive. Okay, and obviously from this difference here, we knew it was greater. Okay, so in that case, since this value is greater than 2, we say we consider this an unusual amount for the burger. So we're just saying like, yeah, and when we talk about the Sonic burger, we need to take it into special consideration because it has so many calories in comparison to the others, right? It's very unusual, very, very weird, very strange. Okay, all right, okay. So, anyways, what I just wanted to show you really quick before we move on to our next topic is how you could use StatCrunch to create a whole bunch of z-scores. And so I just want to show you how to do that really quick. Okay, so say I want to create another column which are just standardized z-scores. Excuse me. So what we do here is I could do data, and I can go into compute, and I could do expression. Okay, and my expression I want to build. Okay, so in here what I want to do is I want to do the calorie amount, whatever the calories, minus the mean. Okay, so minus the mean, which is 620.2. Okay, so I want to do this difference. So every calorie that you have, subtract the mean and divide it by the standard deviation, which is 277.16. Okay, so here I say, I think I just say, so here, okay, we just add it in and we hit OK. And then we could give a label. So we can call it the Z score. Okay. And then we compute. All right. And then there we go. Okay. And then here we have all of our Z scores. And if you go through all of these Z scores, most of the values, see, they're all negative and positive, like close to 0. Right? I really don't see anything that goes beyond 3 or 4. So here we could definitely, so there's a Sonic burger, that's probably the largest one there. Okay, but you could go through here and look at these, but on the Z-score scale, now everything's like on the standard unit, and they're all between like -3 and 4. And just note here that, you know, I kind of didn't do this completely right because I subtracted the mean standard deviation of burger, and I'm applying this to all the data. So really for the z-score, I should have subtracted the mean of all the calories and standard deviation of all the calories. But I just want to show you that nifty trick that we could do with StatCrunch, okay, as far as creating more data, so we could do more analyses. Okay, but what we're going to get into next is summaries for skewed distributions. We're going to get into 3.3, but I'll go ahead and take a break right now and have you do a You're Up section.